The both organizers, Professor Wu and Professor Li, for the kind invitation. And this is the fourth workshop between our two institutes, and I have already participated in 3. And this is my first time in KAIST. So I wonder, there was a Chinese saying that you cannot do the bad things for 3 times, otherwise you will be punished. But but I think for the good thing, we can do it. We can repeat more than 3 times. Okay. Today there is no pointer. Today I would like to talk about some joint work with Mamadou Diagne, who is now postdoc in UC San Diego, and Pepe Shang, she is assistant professor in Tongji University. And the problem that we will discuss is about the feedback stabilization of an extruder model. And this model is the topic of this model is the modeling part is the main topic of the PhD thesis of Mamadou Diagne. Okay, this is the outline of my talk. Let's move on, since we are close to lunch. So, what is the extruder? Extruder is a kind of barrel or a tube. Here is the entrance of the tube, and there is a die which is located at the exit of the tube. So the die is designed to configure the shape of the mixture that was driven by the screw, which is rotating inside, and the mixture which enters the tube here, and it's driven, it's flowing along the tube until the exit of the extruder here. And along the tube there is some heating or cooling system along the whole tube here, and which can be used as control in our control problems. And the rotation speed of the screw is another parameter which can be used as control in our model. So there is some general description about this model. So the extruder is very interesting because there is some modular geometry that allows to control, which is important in application. And these extruders are very common in food industry and also in chemical industry. When one needs to produce some mixture or some food, taking for instance, if you want to produce some Italian pasta with good taste, you need to control the extruder so that the mixture which flows out of the die has a special shape with a good taste. And another important phenomena in this model is the filling ratio of the mixture along the tube can be less than 1 at the near the entrance of the tube, and the filling ratio near the die is completely identically 1. This is one important phenomena. Another thing is that there is a very thin interface between these two zones, which we use partially filled zone, PFZ, and the fully filled zone, representing these two different zones. And as a first attempt to study the well-posedness of this model and trying to control this process, we need some basic assumptions. The first one is to say that the flow is 1D and strictly convective. That means we ignore the heat loss effect along the whole process. And there are some assumptions on the parameters that we will encounter in our model. The school pitch and the specific heat capacity and the density and as well as the viscosity are all assumed to be constant. Here I will remark at the end of this talk that the assumption of the constant viscosity is very important in our present study. Okay, there is a more simplified figure showing the model. Here the space variable is x, so this is the entrance at 0 and this is the exit of the tube, which represented by L. And the interface, the position of the interface is notated as a function of T, L, which is determined by the dynamics of the whole fluid inside of the extruder. So it's moving and it's a free boundary. Here are some constants. And the equations in the partially filled zone are described by a system of conservation law or balance law. The first two are conservation law. Fp is the filling ratio. So the first equation is essentially the conservation of mass, and the second one is about the moisture, so it's the conservation of moisture, and the third one is about the temperature. So we will have some system here which is composed of two terms. One is due to the rotation of the spool inside of the tube. Another one is heat transfer from the boundary, from outside of from the heating system, as I said. And here you see I use the color red for some terms like n. This is the speed of the rotation speed of the spool, which can be used as control when we do the stabilization. And this is TBP, means the boundary, the barrier temperature, which can be used as control as well. Okay. And in the fully filled zone, where x belongs to LT and L, then there is no equation for the filling ratio because it's a fully filled zone, as I said. And the equation for the moisture, again, it's there is no source term, so it's a conservation law. And the temperature the equation of temperature has a boundary, has a source term here, which is again due to these two effects. One is due to the rotation of the spool, and another is due to the heating system along the barrel. Yes, alpha P and alpha F represents the velocity of the fluid flowing in the barrel. Okay. In order to close the whole system, we need some relations at the interface. The first is that we have the discontinuity of the filling ratio, and we have continuity of the temperature and the moisture. So these are conserved along at the interface. And very importantly, we have the pressure relation. I don't want to show too much details, but here we need the assumption that the viscosity of the fluid is a constant eta. With this assumption, we can derive the pressure relation like this, equation 2. Delta P means the pressure at the die, which is the exit of the extruder. P0 is the air pressure because the partially filled zone is open to the air. So this is about the difference of these two pressures. And it can be expressed by these complicated function, which depends on the rotation speed of the screw and the position of the interface L. So finally, oh no, this is not the end of the model. We still need the dynamic of the interface. So it's an ODE, ordinary differential equation. The derivative of L is this is the velocity of the interface when it's moving. So it's given by a function of f. So it depends on L of t, n of t, and the filling ratio exactly at the interface. So with the function, with the ODE and the relation f, we can close the whole system. Of course, in order to study the well posedness, and especially when you want to stabilize this system, we need the usual initial and boundary conditions. These are very normal conditions, and here we use the F in, which is the flow rate at the entrance. So F in of T and M in T and T in T, they are all in red, so it means they can be used as control when we do stabilization again. So here are some problems that we are interested in. First of all, we study the well posedness of the system. So here I write open loop system and closed loop system. When you choose a control which is a function of t, then we say the system is an open loop system. If you choose the control which depends on the solution, a part of the solution of the system, then we call it a closed loop system. And the dependence of the control with respect to your observers are always named as feedback law. The designing of feedback law is the main goal of your control designing. So of course you need to find practical and easily used observers, then you construct a suitable feedback law, and the aim of stabilization is to drive the solution of this system to be asymptotically stable under your feedback controls. Another problem is about the controllability. Here I don't want to emphasize too much. If I have time, I can say something at the end of the talk. So as I mentioned, that the model is governed by two systems of conservation law coupled with an ODE. So and they have a free boundary in the original model. So as a mathematical treatment to this model, the first step is to do the domain normalization, so that, for example, for the partially filled zone, we do some change of variable on the variables, so that the domain can be normalized as a fixed one here. And the cost that you need to pay is that now the system becomes more nonlinear. Here you see the nonlinear function f appears in your new velocity function here, and the x variable appears explicitly here again. And we do the same thing, almost the same thing for the fully filled zone. We can have a similar system for MF and TF. And the new initial and the boundary conditions are given by these formulas. And it's it's not easy to find out that indeed in our whole systems we have 6 equations, but indeed the nonlinear part is already closed for LFT, the position of interface, and the filling ratio in the partially filled zone. You see the equation of L and FP, they are closed already here. Once the solution, once we have established the well-posedness of L and FP, we know the value of L and FP, then we substitute these values into the equations for temperature and the moisture, then we can solve them as a linear transport equation. So it's the main difficulty lies in this nonlinear system here. And again, N and F in can be used as a control when we do stabilization. That's what I say, the linear part. So the first theorem about concerning the well-posedness is something like that. We studied the problem near the equilibria, LE, NE, and FPE. And if the initial and the boundary data, they are not far from the equilibria, then the solution can survive for some time. And we can have an estimate of the solution whenever it exists. Okay, and the solution of FP is now in the class of Lipschitz continuous class here. And the second theorem is that saying that if the initial and the boundary data are in H2, then we can, together with some compatibility conditions, then we can have a solution which is continuous in time and H2 in space. And the third theorem is about the existence and uniqueness of the solution in C0L2 for the moisture and temperature, and we can have the usual estimate. Now let's move to the stabilization part. For some practical reasons, we cannot measure directly. We cannot measure directly the position of interface LT and the filling ratio FP, but a reasonable observer can be the pressure and at the die. So equivalently, because this is the air pressure, which is known as a constant. So what we can observe is the value of delta P. So if you want to design a feedback, you need to choose a function n. You choose the control nt as a function of delta P, and as well. You choose f in as a function of delta p as well. And usually people like to use the linear proportional feedback law like 9 and 10. So the question of stabilization is to find suitable constant K1, K2 such that the solution L and LFP, which converge to the equilibria LE and FPE as time goes to infinity. And we note that the pressure relation is written as equation 11. So once you observe the value of delta P together with these feedback law 9 and especially 9, you observe the value of delta P, and together with the feedback law 9 and the pressure relation 11, you have you can solve here, you can solve the function nt and the delta p here in terms of the unknown function lt, you see? So in this way, even though the observer is indirect, but together combined with the feedback law and the pressure law, it's indeed it's transformed to be a direct observer, you see? And again, f in of t can be expressed by a function of lt. So finally, the feedback law becomes the feedback of the solution itself. Okay. And here is the closed loop system. I write it again, and you just remind you that n and f in, they are all function of lt. And our main theorem about the stabilization is saying like that. There are some constant a1, a2, a3, b1, b2, which is determined by the nonlinear function f and p and the value of the equilibria. Then, if we can find constants k1, k2, real constants k1, k2, such that 13 and 14 are true, then the nonlinear, then the closed loop system under this linear proportional feedback law is locally exponentially stable, which means that if the initial data are close to the equilibria, then you use these feedback control 9 and 10, then the solution goes to the equilibria exponentially fast as time goes to infinity. So we need to, these are 13 and 14 are the main criteria to our stabilization result. And here we have a proposition concerning the criteria, that the criteria 13 and 14 is not true if and only if the coefficient a1, a2, b1 satisfy this inequality. So on the contrary, if the red inequality, the red term, the red condition is not valid, then we can find the suitable K1, K2 such that the system is stabilizable. Okay, and fortunately, the practical parameters implies that A1 is negative, so we can manage to stabilize the model. The ideas for the proof I just show is to construct a strict Lyapunov function. So essentially, the Lyapunov function is, you see, is an weighted H2 energy for Fp, the difference of Fp, and the square of Lt. So the main idea is to prove that the derivative Lt is strictly negative when if you choose a suitable constant A1, A2, A3, and gamma 1, gamma 2, gamma 3. And this kind of weighted L2 energy is introduced by Jean-Michel Coron, who is a professor in University of Paris 6, to study the stabilization for many conservation laws like Saint-Venant equations and some others. And if K1, K2 exist such that 13 and 14 are true, then finally we prove that the Lyapunov function is really a strict one. With this estimate, we can easily prove the exponential decay of the energy. Okay. And for the stabilization of moisture and temperature, which is relatively easy because they are linear transport equations. So you can choose again the feedback law as a linear proportional one here. And for the observer of the moisture equation is the moisture at the exit of the extruder. So again, by using some Lyapunov approach, we can prove that it's exponentially stable under this feedback law. While for the temperature equation, there is two system here. So, but the good thing is that we still have some feedback control as the barrier temperature, which is due to the heating or cooling system. So again, we use these three feedback control to stabilize the temperature equation. This is the main idea of the proof. And as supplementary to the theoretical results, we also did some numerical simulations. And the typical equilibria can be 0.6, and these are all, and the position of the interface at the beginning, at the equilibria is 1.37 meter. And here are some equilibria for the moisture and the temperature. And the initial data is chosen like this. And finally, the feedback gain, the constants that we design in our proportional feedback law is given by K1, K2, K3, and K4. So here is the simulations. This is the simulation for the moving interface. So you see it goes to the equilibria 1.37 very fast. And this is the H2 norm of the difference between the real filling ratio and the equilibria. So it goes to 0 very fast. And this is a 3D plot for, this is a time evolution, this axis. So, and this is time, which is not clear. This is the tube, the extruder. So you see the position of the interface goes to somewhere here. This is 1.37, the equilibria position. Okay. This axis is the filling ratio, the filling ratio part. And you see the simulation of the moisture and the temperature. No, the difference of the moisture and the temperature with respect to their equilibria. So they are both going to 0 very fast. Here is the conclusion. We studied the well-posedness and we proved the exponential stabilization by some natural feedback control. The proof is mainly by Lyapunov approach. The main novelty is about that the PD-OD nonlinear coupling modeling part, and there is a free boundary in our problem, and the feedback control is designed for indirect measurements. And for some future perspectives, and the first one is rapid stabilization. Here we only prove that there exists an omega such that the energy decays at the speed of e to the minus omega t. And the rapid stabilization is saying that for any fixed omega positive, we can find a suitable feedback law such that the solution or the energy decays at exactly the decay rate that you require. This work has been done recently. And concerning the controllability results, the aim of the controllability is not to to drive any initial data to desired final data at a fixed time t, finite fixed time t. And you can use some classical method like linearization and combined with some fixed point argument to derive some controllability results. These are almost done recently. And there are two more practical and important questions. One is about that. One is about the distributed viscosity case. Here I said the constant viscosity assumptions simplifies a lot our models, because the filling ratio and the interface equation are decoupled from the moisture and the temperature equations in our study. And in practical situations, the viscosity depends heavily on the value of moisture and the temperature. So if we move forward to study this case, the whole systems are all coupled together, and it will be much more complicated. But I think we can do the similar works, even though it's more complicated. And the heat diffusion is neglected in our study, and of course it's more interesting to add some heat diffusion for the temperature equations. So I think I should stop here and wish you all have a good appetite. Thank you.